Very good afternoon, one all present here. I'm going to talk on the silicate coated upconverting nanoparticles for optical and diagnosis applications. Uh, See, the nanoparticles are attaining a lot of attention due to its peculiar properties, especially the upconverting nanoparticles, because it has the special properties. It has a different chemical properties, physical properties, mechanical properties, and so on. Before getting into the topic, just I want to give a preamble of my laboratory, which is placed in Anusandhan Kendra, SASTRA deemed university. My lab name is Hybrid Materials Laboratory, which can be abbreviated as HML. We work on basically a porous materials. You can see the picture here. Don't think that I'm working on this particular vegetable. We get inspired by nature, right? So it shows the porous structure. You can see, right? Porous structure, ordered pores, and there is drug loaded inside, and the functional group on the surface. Same way we work on porous materials. Porous materials like mesoporous silica, titanium, metal and metal oxide based, organic based porous materials. We use these porous materials for various applications. And secondly, we also work on luminescent materials, the topic of the day. So I'll be elaborately talking about this, the luminescent materials later on in the upcoming slide. And moving to the next work, what we do in our laboratory, the sensor, electrochemical sensor. We make various electrochemical as well as optical sensor for sensing various chemicals, toxic chemicals present in various products. Especially we work on the sensing of toxic chemical present in cosmetic products. Again, look at the animated picture. See, he or she, after applying all the cosmetic products on the face, he is looking at the mirror. She or he can able to see only the paraben present. See, paraben is being used as a preservative in the cosmetic product, which is highly toxic. So we have developed a particular interfacing material that can sense the paraben with high sensitivity and selectivity. And the next work, what we do is post-based silica materials. It is nothing but a hybrid organic inorganic silica-based materials. The diameter of the post is only 2 to 3 nanometer. So it can be used for various biological applications, especially in the drug delivery application. Within the 2 to 3 nanometer diameter, you can just place 8 functional groups. If you want to increase the functional groups, you can go for dipose, tripose, tetrapose, and so on. Or you can also cross-link the post molecule and get like a framework. So you can use it as a drug delivery system, drug delivery vehicle. We currently work on various post-based materials. We have also developed a very first porous material out of this post-based material. At last, we also work on the diagnosis. I'll be talking about this diagnosis also in the next slides. Right? You can also go through this website. You can just get to know our publications and the people working in our laboratory, and also you can just watch videos in the Hybrid Materials Laboratory YouTube channel. Right? It looks like it is all not interconnected, but it has connectivity. We use the porous material for the luminescence applications. We also use the porous material as an interfacing material, also post as an interfacing material for electrochemical sensing applications. Also, we use the porous materials as well as the luminescent nanomaterials for diagnosis applications. And coming to the topic of the day, which is the luminescent materials, we work on 2 different luminescent materials. One is upconversion nanomaterials, other one is down conversion materials. Basically, it is only these 2 types available, right? Down conversion and up conversion. In the case of down conversion, I want to show you a picture. This represents the LED. See, we use a lot of LEDs for indoor and outdoor applications. Conventionally, we use gallium nitride or indium gallium nitride kind of a semiconducting material, which will eliminate blue color. We need to convert that blue or near ultraviolet color into white. So we need phosphor on the top of the LED. Exactly on that phosphor we work on. But there are 2 problems associated with this conventional LED system. One is the conventional phosphor, which is nothing but the cerium doped yttrium aluminum garnet. will be giving only the green and the yellow color. It doesn't give enough red spectral components. That is first problem. The other problem is the phosphor is completely attached on the LED. So what happens, because it eliminates blue or near ultraviolet due to the electroluminescence process, heat will be produced. Due to that heat, the thermal quenching may happen. So because of the thermal quenching, the quality of the phosphor will come down. So color will get faded off. So these are the two important problems associated with the conventional one. So we work on remote type phosphors, silicate based phosphors to overcome these problems. One is, the first problem is production of cold white. See, the oxyrium will produce only green and yellow, not enough red spectral components. So it produces only cold white. I mean, the cold white is nothing but bluish white. So, but we need a warm white, which is nothing but reddish white. Why do we need warm white? Because we are just living under sunlight for so many years. The sun has enough very huge amount of red spectral components. So we need a phosphor which should compensate that red spectral components too. We work on various silicate based phosphors that will actually doped with the europium or some other rare earth elements. So it will give you enough red spectral components. So that challenge is almost done. And other one is the thermal quenching. The conventional LEDs, if you look at just flashlight of your mobile phone, you can see yellow color. The yellow color is nothing but the oxyrium. The oxyrium is completely attached on the LED. So the thermal quenching will happen. So what we do, we are just making an independent transparent film. That film will not be physically attached on the LED. Instead, we will be keeping particular distance between the LED and the phosphor. So that temperature will not attack directly the phosphor, so that the thermal quenching will be avoided. Only the light hits the phosphor, that phosphor will give the yellow plus red spectral components and will come as warm white. Right. The second one is the upconversion nanomaterials. We work on upconversion nanomaterials and for various applications. Before getting into the topic, I want to tell you what is upconversion. So probably we all know what is down conversion. It's nothing but having electron in the ground state. By just absorbing the radiation, it gets up into the excited state. Right? Once it gets excited, it is unstable state, so it should come down. By losing some energy, it will come down and will be emitting the radiation. This is what the down conversion. Right? The amount of energy given initially for the excitation will not be coming at last. Right? There will be loss of energy always there. The energy loss may be due to the energy transfer from the host to the guest, or else the transfer in between the host, right? But in the case of upconversion, initially it will be in the ground state, and then by absorbing the energy, it gets excited, and there will be another energy level, so that it can give the upconversion. Because in the upconversion, the excitation will happen at longer wavelength. I mean the lower energy, but the emission will happen at higher energy, shorter wavelength. So there will be energy gain should happen. It is really impossible, right? So there will be another energy level next to the first excitation level. So by absorbing another radiation, it gets excited once again to the stage 2 and then emit back, so that you get energy gap. Mechanism proposed. One is the excited state absorption, which can be abbreviated as ESA. Next one is the energy transfer upconversion, ETU, cross relaxation, photon avalanche, cooperative sensitization upconversion, cooperative activation upconversion, energy migration mediated upconversion. Right? This energy mediated upconversion was proposed recently in the year 2011. And now I want to just explain briefly one by one. First one is the excited state absorption. In this, the electron in the ground level, by absorbing the energy, it gets excited. And you can just understand the meaning by looking at the title, excited state absorption. The excited state, the electron present in the excited state will absorb more energy than will get into the excited level 2, so that there will be energy gain, right? Now it comes down so that you will get the upconversion. In the second mechanism, it is energy transfer upconversion, in which there will be the ground level electrons by absorbing the energy gets excited, so it reaches the energy level 1, excited level 1. Now, the energy from this ion 1 will be taken up by this, the electron present in the excited state 1 of ion 2, right? By taking the energy, it gets excited, so that you will get upconversion here. Right. A third one is a cross relaxation, in which initially the electrons in the ground level, by absorbing the energy, see there are 2 ions used here, both will get excited at different energy levels. Now the cross relaxation happens. Initially, by absorbing another energy, it gets excited, and this energy will be taken up by this excited electron, which is present in the energy level 1 of ion 2, and gets excited to the next another energy level. Now the emission will happen, so that there is a gain of energy. You can see this is actually the energy level, but you got, right, and it gets excited. Now after it gets excited, the ion 1, the electron present in the ion 1 gets excited. Now there will be the energy loss from ion 1 to ion 2. That energy will be taken up by this electron and gets excited to the second energy level. Now once again this comes down by losing its energy, and this energy will be combined with this energy, and again it gets excited. So finally the electron present in the excited level 2 in the ion 2 will come down to give the upconversion. And the fifth one is cooperative sensitization upconversion. It is a very simple process in which the electrons will be in the ground level in ion 1 and ion 2. It gets excited by absorbing the energy, and both energy will combine together and will come from the ion 3, the excited level 1 of ion 3. So we'll get the upconversion. Cooperative activation upconversion is also a simple process in which initially there are electrons in the ground level. Those electrons, by absorbing the energy, gets excited to a different energy level of ion 1, ion 2, and ion 3. And now the excited state, the electron present in the ion 1 will be shared by both ions, ion 2 and ion 3, and gets excited. And now you will get the combined energy to give you the upconversion. Finally, the energy migration mediated upconversion, in which initially the electron in the ground level and gets excited, and then now by utilizing the energy from the ion 1, this gets excited to the energy level 2, and the energy transfer happens to ion 3, ion 4, ion 5, and the upconversion happens. Right? These are the proposed mechanisms. So the various types of upconverting nanoparticles. There are fluorides-based, oxide-based, and oxyfluoride-based upconverting nanoparticles. These are all only host. We need to introduce a guest molecule, guest elements, which is nothing but rare earth elements. We can introduce a single rare earth element or multi-rare earth elements to give the upconversion. The color of the upconversion depends on the amount of guest you introduce, also the number of guest elements you introduce into the host crystal. And you can see there are different preparation methods by which you can synthesize upconverting nanoparticles. Few of them are like co-precipitation, in which you'll be using the precursor of upconverting nanoparticles and the precursors of dopants, and it will be precipitated down. That will be treated at high temperature, and finally we'll get the product. And solvothermal hydrothermal technique, in which you will be using soluble organometallic compounds that will be dissolved either in solvent or else in water. If you dissolve it in solvent, that is solvothermal. In water, it is called hydrothermal. It will be placed inside a closed chamber that will be kept near to the boiling point of the solvent, or else the water, whichever you use as a solvent. Now, due to the pressure, the size, shape, and the structure will be regulated. For any nanoparticle, including the upconverting nanoparticles, size, shape, and the structures are very, very important. And sol gel technique, in which initially you will be preparing homogeneous solution, and that will become gel through the polymerization technique, and then it will be treated at high temperature. You will be getting the product. Thermolysis, it is kind of a heating technique, like it will be heated at a high temperature through the degradation and the decomposition. Finally, we'll get the product. And at last, a computation method, it is just like firing, just decomposing it completely, and you'll be getting the rare earth doped upconverting nanoparticles. And what is the fundamental of emission from the upconversion? See, what decides the emission from the upconversion? There are various factors. One is the site symmetry that will decide the quantum efficiency of upconverting nanoparticle. It means there will be a host made up of the fluoride or oxyfluoride based material. Now, you'll be introducing the dopant there. Now, where exactly the dopant is going to occupy in the host? Which cation going to be replaced by the dopant? It is very, very important. That will decide the efficiency of the upconverting nanoparticle first. Next one is electron phonon coupling. Third one is the crystalline phase, morphology, and size. All will be decided by the synthetic strategy. Fourth one is the interatomic distance between the dopants. See, now dopants will be introduced into a host. Now there will be particular distance kept that will be maintained between the dopants. Now, when you increase the dopant concentration, the distance will be decreased so that the concentration quenching will happen. So it is very, very important to maintain the interatomic distance in a host to get perfect upconversion. Last one is a specific capping ligand and extent of the surface coverage. Now, you may be using a silica coating or any other surface modification on the surface of upconverting nanoparticle. You may be doing it for the particular application. That kind of modification will surely absorb some NIR radiation, so that the NIR amount which is entering into the upconverting nanoparticle will be restricted. That will reduce the emission efficiency. Right. And coming to the modulation, you can just see the left-hand side. Goddess has various ornaments and the object on hand, which is for the various application. Similarly, we can also modify the surface of the upconverting nanoparticle using different functional groups. Like you can just introduce various functional groups, hydroxide, amine, acid, amide, and so on. And you can also link DNA on the surface or RNA on the surface. Can go for aptamers and the peptides, or else polymers, dentamers can be introduced. The charge can be varied on the surface, and hydrophilicity and the hydrophobicity can be introduced on the surface. Drug can be loaded on the surface. Antibodies can be linked that can be used for the diagnosis purpose. Finally, the dyes, any dyes can be used on the surface. These are the different modulations. It depends on the application. Right. And coming to the hydrophobic to hydrophilic changeover, initially what we get the upconverting nanoparticle will have the hydrophobic surface. There will be only a group on the surface. It will have the hydrophobicity. To change into hydrophilic, we can just go for the three approaches. One is amphiphilic coating, in which we'll be using like two groups. One is the hydrophobic tail, other one is the hydrophilic head. Already there is a oleate group which is hydrophobic. When we introduce the hydrophobic hydrophilic molecule into it, there will be a hydrophobic interaction on the surface. You can look at the animation. Hope the animation is running smoothly. So there will be a oleate group here which is hydrophobic. Now we are introducing the molecule, hydrophilic molecule, which has hydrophobic tail and the hydrophilic end. Maybe like this. So this hydrophilic tail will come and get attached on this, and there will be hydrophilic head present on the surface, so that you can make it as hydrophilic. Second one is ligand exchange, in which similarly there will be a oleate group on the surface. Now you can just introduce another ligand group which can exchange that oleate group, right? And third one is a silica encapsulation, in which the silica, the organic silica precursor can be introduced. That will get condensed and polymerized on the surface. It will become silica shell on the top of the upconverting nanoparticle. Right. Coming to the application, it has various applications. Like it has passive applications. It can be used for fluorescent imaging, or else magnetic imaging, or PET imaging, or like active way. It can be used as a targeted drug delivery system. it can be capped with the silica. Silica may have porosity. The porosity can be used to load the drugs, and you can just link a functional group on the surface of the silica. That functional group is nothing but the targeting moiety. Now, when it enters into the body, it can go and target a specific region where we need to deliver the drug, and that drug can be delivered there. It can be through internal stimuli or the external stimuli. The internal stimuli can be managed with the pH change or the temperature change. But the external stimuli will be maintained by the external light source. Next one, the upconverting nanoparticle will be used here as to track the material. Like, you can use NIR radiation from outside. You can easily track where it exactly travels. Next application is a sensor. Optical sensor and the electrochemical sensor can be used to sense various molecules. Diagnosis purposes, optically it can be diagnosed, or magnetically it can be done. Next one is a bioimaging. To image the biomolecules you can use. Therapy, photodynamic therapy or photothermal therapy, or security applications. You can look at the bottom of the slide, the different colors. It depends on the dopants and the concentration of the dopants. You can get any colors out of this upconverting nanoparticle. Coming to the modulation versus application, here I'm showing you some of the applications for which you need to modify with a particular molecule. For sensor application, you have to go for ligand exchange in the mesoporous silica shell. For bioconjugation, you have to go for amphiphilic molecules, silica coating and the ligand exchange, and so on. You can see the advantages later on. I will be sharing the slides with you. Next, coming to the chemistry of silica encapsulated upconverting nanoparticles. So, the silica encapsulation has a various application, how it can be encapsulated. That is what. See, there are upconverting nanoparticles here. Now, through the reverse mini emulsion silica deposition, you can just deposit silica on the surface, and using the Aptamer aminopropyl triethoxysilane, you can just introduce amine on the surface. The succinic anhydride can be used along with the DMF dimethyl formamide to introduce acid as a functional group. Now, it is easy to link amine on the surface. When you just use amine terminated DNA or RNA, whatever, the amine can go and attach with the acid by eliminating water molecule. So you'll get amide linkage there. You can link any kind of molecule. What are the advantages of silica encapsulation? It actually gives you the stable suspension. If you go for only the upconverting nanoparticle based suspension, it cannot be stable because the surface area is very high. Now, the aggregation may happen, so the silica capping will actually avoid the aggregation. So stable suspension is possible. Next one, possible to introduce a chemical functionalities for biomolecule targeting because it contains various functional groups on the surface, OH, or you can modify it with amine, acid, anything. And hydrophilicity and hydrophobicity can be tailored, inert, highly inert, and it is biocompatible. And you can also go for mesoporous silica shell on the surface of upconverting nanoparticle, which will have very high surface area to load huge amount of drug on it. And you can also keep a gatekeeper, which can be triggered using internal or the external stimuli. And these are the different upconverting nanoparticles we make in the laboratory. You can see SEM pictures, the various morphologies of upconverting nanoparticle. You can look at the TEM image. You can see the silica capped upconverting nanoparticle here. What is the need of upconversion in the biomedical application? It gains a lot of attention only in the biomedical application because it gives high penetration. Now, if you use a conventional luminescent materials, which is nothing but a down converting materials, you need to pass UV radiation or near ultraviolet radiation. As our cells are made up of organic molecules that will absorb all the UV radiation. So it cannot penetrate. So the bioimaging is possible in vitro level, but in vivo level, it is impossible. So if you go for upconverting nanoparticle, the penetration is possible. When you pass NIR, near infrared radiation, that can easily penetrate into our body, it can reach the material. So that optical imaging is possible. Second one is silica that gives a less toxicity. It is highly biocompatible. Next one is PDT, photodynamic therapy. That is also one of the advantages because you can have a porous silica on the surface. Just consider this is upconverting nanoparticle having porous silica on the surface. You can just introduce photosensitizer into the porous silica. Now, it will be targeted. Now, once it targets the specific region, you can just pass NIR radiation. This NIR will convert this. Actually, NIR will be converted into the visible light by this upconverting nanoparticle. That visible light will be taken up by the photosensitizer, which will produce a reactive oxygen species. That reactive oxygen species will kill the disease cell. This is one way. Other way, it is through thermal therapy, in which it will be also targeted. Once it is targeted, the nanoparticle which is already embedded into the silica shell of the upconverting nanoparticle will be triggered. Like it will have the absorption efficiency, visible light absorption efficiency, so that the temperature will be produced by using that temperature, the disease cell can be killed. And coming to Silica Caped Upconverting Nanoparticles for diagnosis. The Silica Caped Upconverting Nanoparticles are used for various diagnosis purposes. I'm showing a few here. One is optical way, it can be done. Other one is a magnetic way. The last one is the electrochemical way. In the optical way, the low energy will be passed, the high energy will be given at last. So by looking at that high energy or the shorter wavelength emission, we can easily do the diagnosis. The second one is the magnetic way, MRI, there we can use it as a contrast agent. The external magnetic field will be applied, so the magnet will be actually triggered by the external magnetic field, because it will have the super paramagnetic property. So you can image it through magnetic way too. Third one is the electrochemical way. There will be change in the current using by sensing the change in the current, you can easily do the diagnosis. I'm just showing some here. This is the upconverting nanoparticle linked with the antibody. This can be used to diagnose, particularly sense antigen. Right? The antigen can come and get attached here. So when it comes out, if there is a color, yes, it has antigen. Next one is the aptamer based. There is an aptamer here linked. That aptamer is specific to a particular DNA or RNA. So by checking its change in the color or the intensity of the color, you can easily predict if there is any antigen present or DNA or RNA present. Next one is an antigen loaded upconverting nanoparticle. So this can also be used for diagnosis purpose. And next one is the antibody loaded upconverting nanoparticle and magnetic nanoparticle linked with the antigen. Right? This can also be used. Next one is aptamer linked gold nanoparticle and the aptamer loaded upconverting nanoparticle. See, there are two aptamers used. Both the aptamers are specific towards a particular RNA or DNA. Now, initially, the magnetic nanoparticle link with the particular RNA, and again that RNA or DNA will link with this aptamer too. So when it comes out, the upconverting nanoparticle will give you light, and that will show you the presence of particular DNA. And also you can use gold nanoparticle, magnetic nanoparticle in the quantum dots. And I'm just showing you here what we do in our laboratory. See, we just take upconverting nanoparticle and the magnetic nanoparticle by using the TOS, the precursor of silica. We just cap on the surface. So we get a silica shell. You can see the surface, it contains OH groups, and by using GPTMS, glycidyl, so you can look at the name here. It is actually basically silica based molecule, and that will get linked on the surface OH groups, and you will get glycidyl group on the surface. Now we can use amine molecule, which is amine terminated amine molecule. You can just link it. Now we can go for aptamers, aptamer 1 and aptamer 2. See, these two aptamers are specific towards a particular DNA. For example, if you want to do the diagnosis for the recent SARS-CoV-2 virus, see, it contains RNA. So we need to initially take the RNA, we need to take the swab and separate the RNA. That RNA will be actually converted into DNA using reverse transcriptase PCR machine. And finally, it will be amplified. The particular area will be amplified. amplified DNA will be there finally. So to that particular DNA, when if you choose the aptamers, 1 and 2, both are different but specific towards the single DNA strand. Now, once you get the aptamer at the end, it can be taken for the diagnosis. Now, initially we are introducing the aptamer 1 introduce upconverting nanoparticle. Now the DNA will be linked, and then next we are taking the magnetic nanoparticle which is linked with aptamer 2. Now it will also link with that DNA. Once it is done, you can use a magnetic bar to take out, and you can just go for the luminescent analysis. Just pass 980 nanometer NIR radiation, so you'll get a green emission. There will be difference in the intensity according to the availability of nanoparticles there. Right, this is how we can just do the diagnosis using upconverting nanoparticles. And coming to the Aptamer based rapid kit, there are 5 I'm showing you here how it can work. See, there is a strip here. There is a conjugation pad 1 and the conjugation pad 2. Initially, we introduce Aptamer linked upconverting nanoparticle in conjugation pad 1. In the conjugation pad 2, we introduce a Aptamer 2 linked magnetic nanoparticles. As I said already, both the aptamers are specific towards single DNA. Now, we will also use a magnet. I will just explain you why do we need magnet here. When you introduce a sample here, probably a swab sample which is dissolved in a PBS buffer, once it is introduced, it will just go through the strip and it will cross the conjugation pad 1 where that DNA will come and get attached on the aptamer. And then it will cross the conjugation pad 2 where again the magnetic nanoparticle will be attached. As the mass increases, it cannot move on the absorbent pad. So we use a magnet to just drag it so that you will get the spot here. When you use the NIR light, initially you need to wait and then find it is red indication because there is no change in the color. Now there is change in the color. Green color in the presence of NIR, it means it is positive. Green indication, right? The mechanism is simple. Initially, the antigen, the RNA, the DNA gets attached with the upconverting nanoparticle aptamer, and then again with the magnetic nanoparticle and coming up. Next, initially in the conjugation pad, we introduce aptamer linked quantum dots, and then another line with the aptamer introduce upconverting nanoparticle. Another line we make using a control upconverting nanoparticle. Right? It is made on the absorbent pad. Now, when you introduce a sample, it gets absorbed on the pad, it crosses the conjugation pad and comes to these lines. And if you pass the NIR radiation, initially you need to wait. And if you get only red indication in the control, it is negative. If you get red indication in the test line also, it means the patient is positive. The mechanism is simple here. Initially in the conjugation pad, the RNA, the DNA will be linked, and once it crosses the first line, if there is antigen present, upconverting nanoparticle will be linked. So once the upconverting nanoparticle is linked, in the presence of light, that will give you the green color in the presence of NIR. That green color will be taken up by the quantum dots to give red color. So if there is red color, it means there is a presence of quantum dots. There is a presence of quantum dots. If there is no red indication, it means there is no quantum dot present. So the test is negative. The next type of aptamer-based rapid kit has a conjugation pad, and in which there will be aptamer-based upconverting nanoparticle, and there will be single line which has control aptamer. So another line which has the capture aptamer. See, now there are 2 different aptamers, control aptamer and the capture aptamer. When you introduce a sample, it crosses a conjugation pad and reaches the lines. And once you eliminate the NIR light, wait and then check. If you get a green indication, the capture aptamer, it means negative. And if you get green indication in the control aptamer, it is positive. The mechanism here, initially the DNA or the RNA comes to the conjugation pad, and that will get attached with the aptamers, that will move on, and then it gives the change in the color. So it gets attached, and then it gets attached with the nanoparticle if there is no antigen. So it gives only the green color here. If it gives green color here, it means this aptamer is specific for this DNA or RNA. Right? This aptamer is specific for this one, this secondary aptamer. Right? Next way, it is antibody-based rapid kit, in which you will have a gold nanoparticle introduced, antibody in the conjugation pad, and line which is nothing but loaded with upconverting nanoparticles introduced with the antibody. Right? Antibody is specific for that particular antigen. When we can also introduce the control, only the upconverting nanoparticle. Now, when you introduce a sample, it crosses the conjugation pad and apply the NIR, wait, and see if you get a green color on both strips, and it is negative, both lines, it is negative. And if you get only red indication in the test line, it is positive. The mechanism here, initially the antigen comes out. When it crosses conjugation pad, that antigen will be caught by the antibody attached with the nanoparticle, and then it moves on, and the upconverting nanoparticle which is attached with the antibody will get attached on the antigen, so that you will get the red indication. And coming to the challenges and future scopes, so there are various challenges associated with this upconverting nanoparticle based research. If we can able to address all these, we can get a lot of research topics. First one is the increased functionality and biocompatibility. See, we coated with the silica or some other molecule to get the biocompatibility. If we can able to increase the functionality and the biocompatibility for the upconverting nanoparticle, we don't need to use any functional groups or any other capping agent on the surface, because the capping agent always reduces the efficiency of upconverting nanoparticle. The second one is upconversion enhancement through the increase of absorption cross section. See, when it crosses, when the energy crosses, the energy taken by the excited state electrons will be very, very minimized. So if we can able to increase that, the efficiency will be increased. Third one is the capability to improve the activators distribution. The homogenization is very, very important. The dopant, the activator, what we introduce, or the sensorizer, what we introduce into the host, should be homogeneously distributed into the entire system. Otherwise, the concentration quenching will happen easily. There is another challenge. The last challenge is capability to shift the excitation value. These are the challenges. If we can able to address, surely we will get a lot of research topics. Surely it is a very, very hot topic currently, the biomedical application.